July 17th, 1996, 8:31 p.m., East Moriches, New York. TWA Flight 800. 230 people on a routine flight to Paris. 12 minutes after takeoff, a Boeing 747 tore itself apart over the Atlantic. No bomb, no missile, no warning. 2 minutes before the explosion, the captain noticed a fuel gauge acting strange. He mentioned it once. No one responded. That gauge was screaming something at him. But there was nothing he could have done, because the real problem had been building for 25 years beneath his feet. In a fuel tank, the cockpit instruments told him was empty. Inside that tank sat 50 gallons of leftover fuel from the previous flight. Too little to use, too little to measure, just enough to kill everyone on board. How did a tank with almost nothing in it become a bomb that no one saw coming? Earlier that day, this same Boeing 747 had touched down at John F. Kennedy International Airport after a routine transatlantic crossing from Athens, Greece. The flight had been unremarkable. No mechanical issues, no technical faults, nothing written up in the logbook. The aircraft taxied to its gate, the passengers filed out, and the turnaround process began for the next leg, a scheduled evening departure to Paris Charles de Gaulle. The airplane itself was a 747-131, registered November 9, 3119, delivered brand new to Transworld Airlines in the fall of 1971. By the summer of '96, it had accumulated roughly 93,000 flight hours across more than 16,000 pressurization cycles. 25 years of continuous service. In commercial aviation, that kind of age is not unusual. Large transport aircraft are designed for decades of operation, and by the mid-90s, the industry had tightened its aging aircraft programs significantly, especially after the Aloha Airlines fuselage failure back in '88 had revealed how structural fatigue could accumulate in ways traditional maintenance had not anticipated. So this 747 was being maintained under the latest continuing airworthiness standards. Its structure was monitored, inspected, and cleared. But not every system aboard an aging aircraft received the same level of scrutiny. Some things degraded in ways that no one was looking for. The incoming crew for the Paris flight was deeply experienced. The captain in the left seat was Ralph Kevorkian, 58 years old, with over 18,700 hours of total flight time and 31 years at TWA. In the right seat sat Captain Steven Snyder, 63, serving as Czech airman, with more than 17,000 hours of his own. Behind them at the flight engineer panel, an instructor and a trainee brought the total cockpit experience to well over 50,000 hours. This was not a crew that would miss anything obvious. In the cabin, 212 passengers settled into their seats alongside 14 flight attendants. Some were headed to Paris for vacation, others were connecting onward to Rome. A group of high school students from a French club in Montoursville, Pennsylvania, filled several rows near the back, chaperones counting heads. Flight attendants moved through the aisles, stowing bags, checking seat belts, closing overhead bins. Through the cabin windows, the summer sun hung low over the tarmac. From the outside, this turnaround looked like the thousands that had come before it. During refueling, the ground crew loaded all the fuel the Paris crossing would require into the wing tanks. The 747 was only about half full of passengers, well within range, no reason to top off every tank. That meant the center wing tank, a massive structural cavity built into the wing box beneath the cabin floor, received no fuel at all. But the word empty was misleading. Roughly 50 gallons of residual fuel remained inside from the Athens flight. The tank's total capacity was close to 13,000 gallons. 50 gallons amounted to less than 0.5%. Spread across the floor of that cavernous space, it would not even form a visible pool, just a thin film clinging to structural ribs and low points. The fuel pumps could not reach it. The cockpit gauges could not measure it. As far as the crew was concerned, the center tank was dry. While the fueling was underway, a small anomaly surfaced. The fuel tank's automatic volumetric shutoff valve triggered early, stopping the fuel uplift before the required amount was on board. A TWA mechanic reset the circuit breaker to override the shutoff and completed the fueling manually. Maintenance records would later show that this aircraft had logged multiple shutoff valve issues in the weeks before. No one treated it as anything more than a nuisance. But it could have been a whisper from the same electrical system that was about to fail catastrophically. Then, another delay. A passenger's bag had been loaded into the cargo hold without its owner being confirmed on board, a security protocol born from the bombing of Pan Am Flight 103 over Lockerbie 8 years earlier. The hold was reopened, the bag identified and pulled, then put back when the passenger was found already seated in the cabin. After that, a disabled service vehicle blocked the aircraft from pushing back. The crew and passengers sat at the gate, waiting, while ground personnel scrambled for a tow truck. Throughout all of this, the airplane's auxiliary power unit in the tail kept running, feeding electrical power and bleed air to 3 air conditioning packs. 2 of those packs sat directly beneath the center wing tank, separated from it by structural panels, but almost no thermal insulation. It was a warm New York evening, 82 degrees Fahrenheit. The packs worked hard to keep the cabin cool, and they discharged their excess heat straight into the structure above them. The nearly empty center tank began to warm. Inside that tank, those 50 gallons of residual fuel were now in contact with air flowing through the tank's vent system. As the temperature climbed, the liquid fuel began evaporating, mixing with the surrounding air, gradually increasing the concentration of jet fuel vapor within the tank. The mixture was quietly drifting toward what engineers call the flammability envelope, the narrow range of fuel-to-air ratio where vapor becomes explosive. Below that range, the mixture is too lean to burn. Above it, too rich. But inside that window, even a tiny spark carries the force of a grenade. And here is the part that makes this so difficult to accept. Jet fuel in its liquid state is remarkably stable. You can drop a lit match into a bucket of jet fuel and the match will go out, the same way it would in water. But when that same fuel turns to vapor and mixes with air in just the right proportion, it becomes one of the most volatile substances you can put inside a metal container. After 2.5 hours of accumulated heat, the vapor inside that tank had crossed the threshold. The center wing tank of TWA Flight 800 was now a bomb waiting for a spark. And the crew had no instrument, no warning light, no procedure that could have told them. To understand why that mattered, you need to know something about how the aviation industry thought about fuel tank safety in 1996. The philosophy was straightforward. Everyone knew that flammable vapors existed inside fuel tanks. Later studies would show that center wing tanks near air conditioning equipment contained flammable mixtures roughly 30% of the time across the global fleet. This was not a secret. It was considered an inherent characteristic of conventional fuel tank design. The solution was not to eliminate the vapor, because that was seen as impractical, but to eliminate every possible ignition source inside and around the tank. Minimize wiring, limit voltage, create alternative paths for lightning, seal off pathways from nearby equipment. If there was nothing to light the match, the vapor did not matter. That was the theory, and it had a hole in it the size of a 747. Back on the ground at JFK, the disabled vehicle was finally towed away. After 79 minutes of total delays, TWA Flight 800 pushed back from Gate 27. The engines started in sequence. The crew taxied to runway 22 right. At 8:19 p.m. local time, the 747 lifted off into the glow of a fading summer sunset and began climbing along a standard departure route over the coast of Long Island. The climb was routine, engine performance normal, systems stable. Air traffic control cleared them to 13,000 feet, then amended the clearance to maintain that altitude. The crew worked through their tasks the way they always did, monitoring instruments, cross-checking indications, staying in contact with Boston Center. But beneath the cabin floor, the situation inside the center wing tank had actually gotten worse since takeoff. As the aircraft climbed, the ambient pressure dropped, and lower pressure reduces the temperature needed to ignite fuel vapor. The flammability envelope had widened. The mixture that was already combustible on the ground was now even more volatile at altitude. At the same time, somewhere within the miles of electrical wiring threaded through this 25-year-old aircraft, conditions were aligning for something else. The Fuel Quantity Indicating System, known as FQIS, used long electrical probes inside each fuel tank to measure how much fuel was present. These probes worked on a principle of capacitance, detecting the difference between air and fuel based on their electrical properties. The system was designed to be inherently safe. The voltage running through it was extremely low, only enough to release about 0.02 of a millijoule of energy. The minimum energy needed to ignite jet fuel vapor was about 1/4 of a millijoule, more than 12 times higher. So even if the FQIS wiring faulted and produced a spark, the spark should have been far too weak to ignite anything. That safeguard sounded elegant. But it depended on one critical assumption, that the FQIS wiring would remain completely isolated from every high-voltage source in the aircraft for the entire life of the airplane. On the Boeing 747-100, it was not. Unlike McDonnell Douglas, which required FQIS wires to be separated from higher voltage wires by at least 3 inches, Boeing had no such requirement. FQIS wiring was bundled together with high-energy cables in multiple locations throughout the aircraft. Over 25 years of service, insulation aged, cracked, and shaved. Protective coatings degraded. Maintenance activity, repairs, and system upgrades disturbed wire bundles in hard-to-reach places. Inspections were visual, focused on obvious damage, and subtle degradation went unnoticed. After this accident, investigators would examine 26 in-service airliners of various types and ages. What they found was alarming. Metal shavings left behind from maintenance were discovered inside wire bundles. Insulation damage was common, even on nearly new aircraft. On several planes, wires had previously arced, melted together, and self-extinguished without anyone ever noticing. The wiring inside commercial aircraft was far more compromised than anyone had assumed. And there was one more factor. Inside the center wing tank, the FQIS probes used silver-plated copper conductors. When cracks in wiring insulation exposed those conductors to jet fuel, a chemical reaction could produce silver sulfide deposits. Silver sulfide is a semiconductor. It reduces electrical resistance between conductors, which increases the likelihood of arcing. Because the center tank was filled less often than the wing tanks, any contamination had fewer chances to be rinsed away by fresh fuel. Inspections later found silver sulfide deposits on FQIS wiring across the fleet. Boeing had classified it as a nuisance that could cause erroneous gauge readings, not a safety threat, not something that could turn a fuel tank into a bomb. 6 years earlier, a Philippine Airlines 737 had exploded at the gate in Manila under almost identical circumstances. FQIS wiring, center tank vapor, a spark. 8 passengers died. The FAA could have mandated fuel tank inerting or wiring separation after that accident, but that did not happen. The design philosophy held. Exclude ignition sources. Trust the isolation. Keep flying. If you're watching this video right now and finding it interesting, I'd really appreciate it if you hit that subscribe button and give this video a like. It helps the channel more than you might think, and it lets me keep making content like this. Now here is where the story takes its darkest turn. As TWA Flight 800 climbed through 13,000 feet, approximately 10 minutes after takeoff, the cockpit voice recorder captured a moment that investigators would later study over and over. The captain said, "Look at that crazy fuel flow indicator there on number 4. See that?" He was pointing at the fuel flow gauge for the number 4 engine, the outboard engine on the right wing. Under normal conditions, that gauge shows smooth, predictable values. A minor fluctuation by itself was not alarming. No one in the cockpit responded. The conversation moved on. But here is what the captain could not have known. The wiring for that number 4 fuel flow indicator ran through the same cable bundle as the FQIS wiring connected to the center wing tank. That same bundle also carried wires for the cockpit voice recorder and high-power lighting circuits for the upper deck flight attendant station. A short circuit involving a higher voltage wire in that bundle would send energy surging through every wire it touched. The crazy fuel flow reading was not a sensor glitch. It was the electrical fingerprint of a short circuit that was, at that very moment, pushing voltage into the fuel quantity indicating system. The cockpit voice recorder captured 2 brief dropouts of background power noise in the seconds that followed, consistent with electrical arcing near the CVR wiring. At 13,000 feet, somewhere over the dark water south of Long Island, fishing boats rocked gently in the evening swells. Along the shore, families lingered on beaches after a warm July day. None of them were looking up, not yet. The fuel quantity gauge for the center wing tank, recovered later from the wreckage, showed a reading of 640 pounds, more than double the roughly 300 pounds of fuel that had actually been in the tank. Experiments later showed that applying excess voltage to FQIS wiring could cause exactly that kind of spike before circuit breakers had time to react. So a short circuit had occurred. Excess voltage had entered the FQIS, and inside the center wing tank, those probes and sensors, designed to carry almost no energy at all, were now conducting far more than they were ever built to handle. In an environment already saturated with heated fuel vapor, pushed deeper into the flammability envelope by altitude, contaminated with silver sulfide deposits that lowered the threshold for arcing, the only thing left was a spark. At 8:31 and 12 seconds, it happens. A tiny arc, a momentary discharge, possibly released through a silver sulfide deposit on an FQIS probe. The fuel vapor inside the center wing tank ignites. Not a detonation, a deflagration. A flame front races through the tank at subsonic speed, but the energy release is so rapid, it immediately exceeds the structural limits of the tank walls. Inside the cockpit, the crew has no time to react. Not a second, not a fraction of a second. The overpressure tears through spanwise beam number 3, a critical structural element running across the tank. That beam topples forward into the front spar, the structural wall forming the front of the tank and a primary load-bearing member of the entire aircraft. The front spar fractures. It slams into the potable water tanks directly ahead. The spar loses its rigidity. Without that rigidity, the fuselage skin below buckles under the expanding pressure and rips open. Now the damage cascades. With the fuselage skin gone, the structural members around the hole absorb loads they were never designed to carry. The keel beam, the structural spine running the length of the aircraft, fractures. With the spine broken, the fuselage can no longer hold itself together against the bending forces of flight. The skin tears upward and over the top of the upper deck, splitting the airplane in two. The entire forward section, cockpit included, rips away and falls toward the ocean. From the initial spark to the nose separating took 3 to 5 seconds. Those 50 gallons of leftover fuel, the residue that no gauge could read, that no crew could detect, that the system was never designed to worry about, had just destroyed a 747 and everything in it. What remained of the aircraft, the aft 2/3, was now an aerodynamic catastrophe. 80,000 pounds of structure had been torn from the front, collapsing the pitch balance entirely. The center of gravity shifted violently rearward. The wings still generated lift. The engines may have still been producing thrust. The tail still pushed downward. A powerful nose-up pitching moment threw the wreckage into a steep climb. Radar data and simulations later showed that the remains climbed another 2,000 to 3,000 feet, reaching nearly 16,000, as forward speed bled away into altitude. Then it stalled, rolled right, and entered a near vertical descent toward the sea. During those final seconds of climb, burning fuel spewed from the ruptured wing roots into the darkening sky, visible for dozens of miles. Hundreds of witnesses along the Long Island coast saw what appeared to be a streak of light climbing upward before a massive fireball. Many believed they had seen a missile striking an aircraft. They had not. Real surface-to-air missiles burn their motors for only a few seconds after launch, then coast invisibly toward their targets. Witnesses to an actual missile strike would see a brief flash near the ground, then an explosion in a completely different location. No one reported that pattern on that night, and when investigators eventually recovered and examined 98% of the aircraft, they found no missile fragments, no high explosive residue patterns, no shrapnel peppering consistent with a warhead detonation. Every piece of physical evidence pointed to one thing: an overpressure event inside the center wing fuel tank. The wings broke apart under aerodynamic loads during the descent. Their fuel tanks ruptured, releasing thousands of gallons of jet fuel into the fire. The tail separated. What was left of the disintegrating wreckage rained burning into the Atlantic Ocean. All 230 people aboard were killed. What followed was an investigation of extraordinary scale. Recovery vessels, divers, remotely operated vehicles, and sonar systems mapped a vast stretch of the Atlantic seabed. Over the course of months, investigators located, identified, and retrieved wreckage scattered across multiple debris fields by both the breakup and strong ocean currents. Ultimately, nearly 98% of the aircraft was recovered. Inside a hangar, the fuselage was painstakingly reconstructed in skeletal form. Thousands of fragments were aligned, mapped, and studied. Fracture surfaces revealed the direction of forces. Soot deposits traced the path of combustion. Deformation patterns showed which structures failed first and which were torn apart as consequences of earlier failures. Metal skin peeled outward from the center tank surfaces, not inward. That directionality was critical. An external blast or a bomb would have driven material inward. This explosion had pushed outward from inside the tank. And here is where the investigation reached beyond the cockpit and into the system that had made this accident possible. Investigators found arcing damage on high-power generator cables in the left wing, cables that had been bundled alongside FQIS wiring, connected to the center tank circuits. More arcing damage appeared on wires routed through an area that had previously undergone structural repairs after a burst water tank, where maintenance had disturbed existing wire bundles. Metal shavings were found within inches of where a missing center wing tank FQIS wire bundle should have been located, in an area with recent reports of water leaks. The exact origin of the short circuit was never pinpointed. Too much wiring had been destroyed or was unrecoverable, but investigators identified multiple locations where it could have occurred, any of which could have allowed high voltage energy to enter the FQIS and reach the inside of the tank. The deeper question was not what sparked the explosion, but why the spark was possible in the first place, and the answer went back decades. In 1963, Pan Am Flight 214, a Boeing 707, crashed in Maryland after lightning entered a vapor-filled fuel tank and triggered an explosion. The Civil Aeronautics Board recommended fuel tank inerting, a system that would pump nitrogen into empty tanks to displace oxygen and prevent flammable mixtures from forming. That recommendation was made 33 years before TWA Flight 800. It was never implemented. In 1976, a Royal Iranian Air Force 747 crashed near Madrid after lightning ignited a partially empty wing tank. In 1990, a Philippine Airlines 737 exploded at the gate in Manila when an FQIS wiring fault ignited center tank vapor, killing 8 passengers and injuring 82. That accident had demonstrated the exact vulnerability that would destroy TWA Flight 800 6 years later. An FQIS wire could arc inside a fuel tank. Excluding every ignition source 100% of the time was impossible. The industry knew it, and it did not change. By the time the NTSB published its final report, nearly 4 years later, the investigation had become one of the most exhaustive in the board's history. The probable cause was an explosion of the center wing fuel tank, resulting from ignition of the flammable fuel-air mixture inside. The most likely ignition source was a short circuit outside the tank that allowed excessive voltage to enter through FQIS wiring. A contributing factor was the design and certification philosophy that fuel tank safety could be assured solely by precluding ignition sources. Families arrived at Kennedy Airport that night, looking for information that would never come in the form they hoped. Personal belongings washed ashore along the Long Island coast for weeks. The 4-year investigation consumed the lives of hundreds of investigators. The wreckage reconstruction, housed in an NTSB hangar, was used for training for nearly 2 decades before finally being decommissioned in 2021. The changes that followed this accident reshaped commercial aviation. Regulators mandated fuel tank inerting systems, technology that pumps nitrogen-enriched air into fuel tanks to keep vapor concentrations below the flammable range. By around 2018, virtually every airliner in service was equipped with these systems. Those 50 gallons of residual fuel that sat unnoticed in the center tank of TWA Flight 800 could never create the same danger again. At the same time, the investigation forced a fundamental rethinking of how electrical systems were maintained over the life of an aircraft. Wiring, insulation, connectors, separation standards, contamination environments, all of it became central to long-term airworthiness thinking. New certification rules required FQIS wiring to be routed separately from high-energy circuits. Boeing, which had no separation requirement before this accident, now had to redesign how its wiring was bundled across its fleet. TWA Flight 800 did not reveal a single hidden defect. It revealed how ordinary conditions, individually unremarkable and widely distributed across the fleet, could interact to erode safety margins until there were none left. A tank that was almost empty, a fuel residue too small to measure, air conditioning packs doing exactly what they were designed to do, wiring that had aged the way all wiring ages, a chemical deposit that no one thought was dangerous, and a design philosophy that assumed perfection in a system that could never be perfect. On a summer evening in 1996, a 747 pushed back from Gate 27 at Kennedy Airport, carrying 230 people toward Paris. 50 gallons of fuel sat in a tank beneath the cabin floor, invisible to every instrument in the cockpit. 12 minutes later, that fuel was no longer invisible. It was the last thing that mattered. If this story stayed with you, please consider subscribing and sharing this video with someone who would find it interesting. Your support is what makes these deep dives possible. Now, the wiring problems exposed by this investigation would later echo in another disaster that shared an eerie number of coincidences with TWA 800. Same airport, same time of day, same day of the week. A different airline, a different aircraft, but a fire that started in the same invisible place, inside the walls, where no one was looking. That story is coming next.